Prof è mutato.
Okay, welcome back, everyone. Can you hear me properly online?
Ottavio, ma mi senti?
Can somebody reply?
Yes.
Mi senti?
Oh, maybe I cannot hear you. No, I do. I should be able to hear you. Can somebody reply if you can hear me?
Yes, we can.
Okay, great. Thank you.
Ok.
Okay, so welcome back to the lecture. I want to start with a small comment from yesterday. Yesterday I showed you the pseudo inverse, but I made a small mistake here with the one that I showed you, actually, because I showed you the right pseudo inverse, which is the correct one if you are getting the pseudo inverse of J. But since J transpose is skinny, it's a skinny matrix, it's a tall matrix, then the pseudo inverse is the one that you see here. So it's a left pseudo inverse. And the way you realize this, it's because the column rank, so the rank of the matrix needs to be full. So it needs to be a tall matrix, and it's a left pseudo inverse because if you add an A here, then you get so it needs to be full rank. Otherwise, this expression here is not invertible. And if you add an A here, then you get the expression back, identity. Sorry, let me close the door. Okay. So are you trying to talk, Michele? Because I cannot hear you.
No.
Okay. Sorry, it was an old message then. Now I can hear you. Okay, so let's move on then. So going back to our panoramic view, we already saw the PID family plus gravity compensation of controllers in the joint space, also the ones, the feedback linearization type of controllers in the joint space. And we saw yesterday up to the PD plus gravity compensation in the task space or Cartesian space. So today we're going to be talking about feedback linearization in the task space. Okay. So remember that computed torque control, it's a specific type of feedback linearization for mechanical systems in Cartesian space. So we're going to work out the equations for computed torque control in Cartesian space. So let's go back to our joint space dynamics. And here I'm not writing explicitly the dependency on Q and Q dot of matrices M, H, and our controller, just for simplicity of the procedure that we're going to do afterwards, and because by now it should be obvious that they do depend on Q and Q dot. And let's start from the assumption that so then the number of task space variables is it's the same as the number of joint space variables. So this means that there's no redundancy in our manipulator. And first, what we need to do to achieve the inversion in the task space is that we need to consider the behavior of the manipulator at the end effector. Okay, so in terms of the Cartesian dynamics. So let's start from definition from our transformation from Cartesian or task space velocity to joint space velocity through the Jacobian. So if we derive this again, we get the acceleration of the end effector of the task space. Remember that we have the chain rule, so we have two terms here. And from here, we can actually isolate q double dot, so the acceleration, the joint acceleration vector. And furthermore, we can use this expression to replace q double dot in equation 1 here on top. Okay. And once we do that, we get this expression for our joint space that, well, from our dynamics equation now. And now we're going to start doing some algebraic manipulations such that we get to a specific expression that will make evident how the joint space matrix and the nonlinear terms behave in relation to the end effector. So first we're gonna left multiply by J inverse transpose. Now here it's important that I make the comment that we are allowed to get the inverse of the transpose because we have a non-redundant robot, so M is equal to N. So J is a square matrix and J furthermore is non-singular. So this is only possible, you can only get J inverse transpose in the cases where you have a non-redundant robot. Okay. So if we do the left multiplication of J inverse transpose, we get this expression here. Now this first term, it's this one. Okay, let me erase this. Then the second one, so this is the multiplication of J inverse transpose times the acceleration. Then this second term, this product here, we moved it to the end here. And then the term here, it's just this one. Okay. And then we multiplied also the other way, so the other side. So just to keep the equality satisfied, we need to multiply both sides of the equation. And let's call this capital lambda. And let's call this mu. And then recall that the torque, it's equal to J transpose F. Okay. So we map from end effector forces or moments to joint torques through the transpose Jacobian. So in order to map back from joint torques to forces, we use the inverse the inverse transpose of the Jacobian. So in the end, what we get here, it's forces at the end effector. Okay. So we have this expression here, which is basically just replacing with the terms. Now here, we're making explicit the dependency on Q and Q double dot and Q dot, sorry. And this equation shows us the dynamics reflected at the end effector level. Okay. And this capital lambda, which is this matrix product, it's the Cartesian inertia, which is basically the joint space inertia seen or felt at the end effector. Again, keep in mind that capital lambda will become singular if J is singular as well. So this means that there's no inversion of the Jacobian. And this is the case for redundant robots. Then we have this vector mu, which is the vector of Cartesian bias terms, which is the equivalent of the vector of nonlinear effects in the joint space. Only this for the Cartesian space. And then we have F as the Cartesian force. Okay. Remember that we're considering P as a Cartesian position in space. Later next week, the professor will do a lecture on orientation control. For now, we're just focusing on position. So now that we have this dynamics expressed in terms of the end effector, we can apply the feedback linearization. And if we choose F to be the approximate Cartesian inertia matrix times an additional input called V plus the estimation of our mu vector of bias terms. And we now assume that we have perfect knowledge of lambda. These are our closed loop dynamics. And as now, since we're doing feedback linearization, these two terms go away. Well, they become zero. And then in the end, we obtain this expression, which is a linear system which is a series of double integrators. Similarly to the ones that we found in joint space, and they are independent and they are unitary mass, as we saw also in the case of the joint space. So as we did in the case of the joint space, we can design a stabilizing controller to reduce the tracking error in all of the double integrators. Just I mean, the main difference between the joint space, well, one of the difference that you have to take into account is that the size of M, it's the size of the task space now, and we're going to design a controller for all of the coordinates in the task space. And this is how we define, similarly to as we did to the way we did in the joint space, our control action with our desired acceleration and our PD term now in Cartesian space. And again, it can be proven, you can prove stability in the case where Kp and Kd are positive definite matrices. Remember that P is a vector, so Kp and Kd are matrices which are positive definite and diagonal, so that you have a control independently for all the coordinates in the task space. So this results in the closed loop dynamics, as you see here on the slide, which turns out to be the error in the acceleration times a derivative term, a proportional term, and a derivative term here. And we're going to call this error E of X, EX, which is the Cartesian tracking error. Okay. So let's write again our equation now in terms of our Cartesian tracking error. And we can prove that this is stable in the case where Kp and Kd are positive definite matrices. And just as a general reminder, you can prove this using the first method of Lyapunov, and then you can only prove stability with Lyapunov. You cannot prove asymptotic stability, because in the end, in your Lyapunov equation, you're gonna get that the derivative it's gonna be negative semi-definite. So in order to prove asymptotic stability, you need to use the Lassalle's invariance theorem. In case you're curious about it. So the final control law turns out to be this one, which is our estimation of the Cartesian mass matrix, Cartesian inertia matrix, and then multiplied by our V, which turned out to be this term here with the proportional derivative action, and then our compensation for the nonlinear terms here. Always using the current joint states that can be measured. We're missing a dot here. I just noticed. Okay. So let's talk about the physical interpretation of this controller. So imagine that you have a manipulator which is now currently balanced by the torques at the joints are balancing gravity. And what's going to happen is that so if you don't use an approach in the task space that gets rid of the nonlinearities related to the task space, what's going to happen is that the inertia at the end effector, it's going to depend on the configuration of the robot. So it's going to depend on the value of Q, and it's going to be variable in the Cartesian direction. So at the end effector, you're going to have different inertias in the X, Y, Z directions. And this is related to what we were discussing yesterday with the professor, that you're controlling basically with springs at each of the joints. And even though if you get rid of the coupling, this inertia that you feel at the end effector, it's gonna feel differently depending on the position at which you are, or the configuration. So if you apply a force in a specific direction at the end effector, the end effector is going to accelerate in a different direction than the one that you're pushing. In general, I mean, it might be the case that your manipulator is in a certain configuration, that the resultant is in the direction that you're pushing, but in general, it won't push in the same direction. Now, remember that we mentioned that when we do the inverse dynamics or computed torque control, so when we do the feedback linearization, we get a unitary mass. So basically what we mean with this is that you get a mass at the end effector level with unit 1, and when you push that mass in a specific direction, it's going to displace in the same direction as you're pushing. And this is because you're getting rid of the dynamics at the Cartesian level. Okay, or you're compensating for the dynamics. I shouldn't say getting rid. You're just compensating for them in the control action. So now let's see the case for redundant manipulators. So now we are in the case where you have more joint variables than task space variables. So our Jacobian is going to be a rectangular matrix, and specifically it's going to be a fat matrix, a long matrix. And of course we know that if the matrix is not squared, then the inverse of the Jacobian does not exist. So we can obtain a input-output decoupling linearization, or an input-output decoupling of our task variables, and also a linearization, but not for the entire state vector, if we replace our inverse transpose with the pseudo inverse of the transpose. So we start from an alternative derivation. So again, we have our joint space dynamics. And now instead of multiplying by J inverse, we're going to multiply by this Jm inverse. And of course, we cannot multiply by J inverse because it doesn't exist. So we do it with this alternative derivation. And this is what we get. So the M inverse multiplies M here, and you get identity. And the rest of the terms, you keep the Jm inverse. So the joint space inertia, the inverse of the joint space inertia matrix. We know that for mechanical systems, the joint space inertia matrix is squared and positive definite. So you always have an inverse of M. And what's more, this JQ double dot, if you recall the derivative, so let's write again the derivative of the mapping between task velocities and joint velocities. If you take again the derivative, you're gonna get JQ double dot, and here we have JQ double dot, and JQ double dot, it's equal to P double dot minus J dot Q dot. Okay, so this is what we're writing here. Let's hope that I'm not in the way of any text. Yes, I am. I'm gonna get rid of this. Okay. So we now consider an alternative expression for capital lambda, and this one exists for redundant manipulators, which is this. So we can say that this exists because we're only taking transpose of the Jacobian matrix, and this inverse, it's only defined if the Jacobian needs full row rank. So this is also something that you need to take into account. So this is our new definition of capital lambda. So if we left multiply our dynamics by lambda, we get this expression here. And so we have lambda multiplied by the acceleration, then you get lambda multiplied by the derivative of the Jacobian times the joint velocities, and then you get lambda times the Jacobian times M inverse, which is equal to what you see on the right hand side of the equation. So here we're rewriting again the same expression as at the end of the previous slide. So this is our vector of bias terms, and of lambda, it's the same as in the case before. It's our Cartesian inertia. And now let's take a look at what's on the right hand side of the equation. So remember that lambda, we define it as this, as the inverse of the multiplication of these three matrices, and then I'm just writing Jm inverse. Okay. So recall that J transpose is a skinny matrix. So to take the pseudo inverse of this one, we need to use this expression. This requires that J transpose is full rank, full column rank. So in order for J transpose to be full column rank, J needs to be full row rank. And this is the left pseudo inverse of A in this case. And this is called left pseudo inverse because if you multiply it by A on the right of the transpose, then you get identity. Okay. So let's write it. Let's write the left pseudo inverse of J transpose, and this is what you get: J times J transpose inverse times J. So if we do this multiplication, you can already see if you add the J transpose on top, what we have here is identity. So let's just expand the pseudo inverse to what we have here. So it's basically just adding J transpose on top. And we know that M, it's a positive definite matrix, and the inverse of a positive definite matrix, it's another positive definite matrix. So we can add in the middle of the expression this M inverse here, and we agree that this multiplication is still identity. And what's more important is that this can be replaced as the inverse transpose of as the pseudo inverse transpose of the Jacobian. Sorry, the transpose pseudo inverse of the Jacobian. And in the end, this expression that we have on top, it's equal to the J transpose pseudo inverse. Okay. So for a redundant robot, our force is going to be mapped by the transpose pseudo inverse times our joint torques. Okay. So these are our Cartesian dynamics now for a redundant robot. And because we have redundancy, there's going to be n minus m joint torques that need to be stabilized with a postural task in using the null space of our J transpose inverse matrix. So we use the torques that do not generate any force at the end effector. So if you don't have any force at the end effector, there's no motion caused by those joints at the end effector level to control the redundant degrees of freedom. So mainly what we want to do is find the portion of U that it's in the null space of our J transpose inverse matrix. And what we mean by this, it's finding the input vector of size in the of the size of the joint space, so it's n, such that its inverse, its transpose pseudo inverse times our input goes to 0. So this means that it doesn't generate any force at the end effector. So just giving it a name, U0, it's going to be the torques that when you multiply them by the transpose pseudo inverse, it would not generate any acceleration at the end effector. So we break our control input into U plus U0. And what we want is that when you multiply this U times this U0, at the end, you're going to get the same J transpose pseudo inverse U. Okay. So we can use our our null space, the null space projector, and which is this one in this case. Remember that this is not identity because J transpose is skinny, and it's a left pseudo inverse. So just bear that in mind. And here we add a UP, which is going to be our input for a postural task. So let's verify that J transpose pseudo inverse times U0, it's equal to 0. So if we multiply J transpose pseudo inverse by our U0 input, what we get is this expression here, J transpose pseudo inverse minus J transpose pseudo inverse times J transpose. And now, because J transpose is a skinny matrix, then this becomes identity. And then you get inside of the parentheses J transpose pseudo inverse minus J transpose pseudo inverse, which is 0. multiplied by our postural torques control action, and this is 0. So we verified that we don't generate any force at the end effector level with this control input. So our final control law becomes this expression right here, which is the Cartesian task, so the one that is going to be in charge of following a trajectory. Remember that V is defined with the desired acceleration and the PD action. And this is going to be in charge of following our trajectory. And then we have here our postural task controller, which is using the joint torques that are not generating any motion at the end effector. So here, as again, I repeat that UP it's the postural task that stabilizes the internal dynamics of the robot, and we can define it like this, which is a PD action for the joints that are being projected by our null space projector. So I'm going to show you a couple of examples. In this one, they're using the null space projector to generate a postural task, but also they're extending this to also consider joint limits, so hard constraints on the joints. So they're coming with a kinematic trajectory in a task space controller that follows a trajectory, but also has a postural task. So here you have the robot that it's tracking a trajectory, and you see that in a certain way is trying to keep the posture, but it also takes into account now its kinematic limits, and then it's just repeating the motion, the circular motion here, and it should come to a stop now. Yeah, this is a work from University of La Sapienza in Roma, from a former student of, well, it's a former collaborator of Professor Alessandro De Luca and Osama Khatib. Then we have this other example in which the robot is commanded, the end effector is commanded to stay in place. And in this controller, what they're trying to extend is that at the end effector level, so they can differentiate between torques related, applied at the end effector. For example, if you're doing a machining task at the end effector, so if you're, let's say, polishing or finishing a small part, in general, when you do collaboration with humans, the human does the polishing and then it uses the robot to relocate the part in a certain way that it fits. So here, the controller that they develop, it's able to identify that forces and torques at the end effector that are related to the machining task. So if you push against the end effector, it won't move. But if you apply a torque just to adjust the posture of the robot, then it will identify that as a torque for posture adjustment, and it would just move, and but trying to keep the orientation of the end, sorry, the position of the end effector, not the orientation. So here you see that he starts by trying to move the end effector, and it's not able to move it. So imagine that that there's a part there, and then he's adjusting the posture of the robot by moving the joints. Here, I think that they're using something called a residual method that is able to identify the torques that are not playing a role at the end effector level. And this is it. So some remarks on Cartesian space inverse dynamics. you can achieve the decoupling in Cartesian space, and in the end, we have this nice interpretation of a unitary mass that you can move in any Cartesian direction based, which is the same as the force that you're applying. However, as we noticed, it is more complex than the computation of the computer torque controller in the joint space. And this is because it's influenced by redundancy, for which it can be solved, as we saw, by adding a postural task in the null space. Also, if there are singularities, then, as we saw in the lecture of inverse kinematics, then we need to implement a singularity robustness to avoid reaching these singular configurations or staying far from those singular configurations. So let's do a small recap on the mappings that we have seen so far. So the first one, which is it's an easy one, it's the mapping that you get by multiplying the acceleration by the joint space inertia matrix, which translates to joint torques. Then if you do the inverse, you go from joint torques to joint accelerations. Then if we look at the Jacobian, we can use it to map from joint velocities to task velocities. But and in this case, we can also, if you take the derivative of that, we can use it to map from joint acceleration to task accelerations. And then we can also use the transposed Jacobian to map from forces in the task space to joint torques. And now that we saw our Cartesian inertia, we can use it to map from task forces, so the inverse of our Cartesian inertia, seen here in the case of the redundant of our redundant robot. So the inverse of this, it maps from task forces to task accelerations, and the Cartesian inertia, which is the inverse of the previous one, we can use it to map from task acceleration to task forces. Okay. Now, an additional note, we can obtain a similar result to the task space computer torque control. Actually, I'm calling here inverse dynamics, but I forgot to change this one because this is, oh no, and never mind, I had it here, joint computer torque control, and this is the inverse kinematics. So we're gonna, so the idea is that we're gonna solve the inverse kinematics at the acceleration level to get the desired acceleration, the desired joint acceleration, and then we can use the joint space computer torque control. So here I'm saying joint space inverse dynamics because we're inverting the dynamics, but it's in fact the computer torque control here. This is the joint space computed torque controller to get our control input U. So let's already start from the redundant manipulator case, and we can start from the Cartesian space acceleration, which is defined by this, and we can get from here. So we can use this expression to get our desired joint acceleration. So remember that here V, in the case when we always linearize the system, B it's equal to P double dot in the case of the task space. Now Now, for those who followed Professor Del Prete's course, he calls V, actually, he calls it P double dot D, right? So this is basically just the equivalent that we're doing here. So because we use V, because it's a new control input that we're defining, we just replace this P double dot D with our control input. Okay. So just in case if you get confused to see a D there, it's just a P double dot D, which is defined by our P double dot reference trajectory plus our PD action. Okay. And then just some other thing that it's important to that I want to tell you is that here you have the pseudo inverse, right? So in the case where J, so for a non-redundant manipulator, so that means that J is squared, you can just simply isolate Q double dot by moving this term to the left, and then you would get P double dot minus J dot Q dot, and then you multiply everything by the inverse of J here, right? Now, this is not what we're doing here with the pseudo inverse, because remember that the Jacobian here, it's a fat matrix. So actually the pseudo inverse of the fat matrix, it's a right pseudo inverse. So actually we cannot just multiply here by J pseudo inverse. So this is not what we're doing here. However, if you substitute Q double dot in this same equation, so if you would substitute Q double dot for in this same equation, actually this satisfies the equation and on the left. So if you would solve it for Q double dot, you would get P double dot equals P double dot in the end. If you want to do it by yourself, you can always do it, but it's true. And this is because there are multiple solutions to this equation, and this is one of the multiple solutions to the equation. And then for our desired joint acceleration, we can always add our null space projector to take care of the joints that are not generating any motion of at the end effector level. So we plug in this expression of our desired joint acceleration into our joint space inverse dynamics controllers to obtain the torques. And this is what we get in our closed loop dynamics. So remember that on the right hand side of the equation, we have all of this. It's going to be our U. And remember, if you go back to the slides of the joint space to computed torque control, you'll see that we're only replacing our new value for Q double dot D in those equations. So again, we need that the Jacobian its full row rank. Otherwise, the pseudo inverse of the Jacobian does not exist, and this is because the so if it's a right pseudo inverse, so it would be J transpose J inverse would not exist. Okay, so just bear that in mind. So this is easier to implement, and mainly because I mean the equations are simpler, and it's faster to compute because you don't need to compute the capital lambda matrix. So let's just verify the closed loop behavior of the controller. So here we have our closed loop dynamics. Okay, remember that these are estimates, but we're assuming that we have full knowledge of the system just to verify the closed loop behavior. So all of these terms, they go away. Then our Q double dot so becomes this expression right here if we replace Q double dot D. And then if we work out all of the products that we have here, oh no, sorry. If we first pre-multiply on the left, so pre-multiply is multiplying on the left, all of our expression by the Jacobian, we get this that we see here. And now here, you see that it's a right pseudo inverse, so this will become identity. And then you get J minus J. So you will get 0 here. And all of these terms, they go away. So in the end, we get this expression right here, which is JQ double dot plus J dot Q dot, which is equal to B. And remember that this is equal to P double dot. So in the end, we get the same as in the previous case when we worked out all of the equations in the Cartesian space. Okay, so this finishes the lecture on Cartesian feedback linearization. Are there any questions? Okay, good. So let's have a 15-minute break. So we reconvene at 6:40. Okay. Okay, so let's start again. So can you hear me online?
Yes, we can.
Yes.
Okay, great, thanks. So now I'm gonna jump to our H2 set of slides because the professor is preparing the lecture of in orientation control. Is finishing, well, he just finished the slides, and he wanted to add some material on orientation control, and he's gonna show you those on Monday. So I'm gonna give you today an introduction to interaction control of manipulators, and just a first naive approach to interaction control.
Yeah, sorry, Octavio, a quick note. Yeah, so in essence, it's just for organizational purposes that we postpone the topic on control of orientation into the next week, but you should think this topic as being exactly logically being taught now, because it's just the angular equivalence of what we explained in the Cartesian task-based control. So this topic on interaction actually would be the logically the last one. So just remember this in your notes.
Yeah, so we just shuffled a bit the order just to manage to complete the things in time and don't have like too much empty spaces in our organization, but also don't be delayed by just because we want to keep a certain order. Okay, so we thought that this might fit best in terms of time. Okay, so let's start. So as I mentioned, I'm just going to give a bit of an introduction to the interaction control methods, and then I'm going to just talk about a very, well, let's say a first approach that dates back from the 90s, and now more modern techniques are based on impedance or admittance controllers that the professor is going to show you on Monday. So let's start by talking about interaction control. So up to this point, we have only discussed control strategies when the robot is in free motion. However, when the robot has to interact with the environment, by interaction we mean manipulate it, or also avoiding collision, or even interacting with other robots or other mechanical devices or people themselves. There is an increased difficulty on the problem, and that is that sometimes we need to know how the object might behave related to our interaction, and modeling the object of the modeling objects. It's a difficult problem. It's actually an open research problem in many groups that do robotics. For example, there are vision-based techniques, there are haptic-based techniques, and modeling the behavior of an object. It's in itself a difficult problem. So what we're going to try to focus now, it's to kind of control or regulate the contact forces that we have with the environment. And some applications related to interaction control of robots. It's when, for example, when manipulators are performing operations on surfaces. So these operations could be drilling, grinding, or deboring. Deboring, it's this operation when you remove like the metal shards or the plastic shards of parts that are just made, for example, like this, they're very sharp. So you need to, these are called burrs, and deboring is removing these metal shards. And you usually do this with sandpaper or with polishing material to remove those. There's also surface finishing and polishing that you can do with a manipulator. Assembly tasks. So I'm going to talk to you about some assembly tasks. I couldn't find a good video about it, but there are some cool, interesting insights on how a robot is able to perform relatively complex assembly tasks. And there are also, in modern robotics, and a very hot topic in modern robotics nowadays is human-robot interaction, and this can be related to, for example, rehabilitation. So here you have it's a kind of game where you have a haptic you have a device in which you need to move an object in a screen, and sometimes you have a task to fit the object with the, so one of those circles, if you reach to see the screen, there are some circles and one of them blinks, and then you need to take the ball using the haptic device that is there, or sometimes the haptic device begins guiding you towards the object, and then little by little you start gaining independence. So for example, if somebody has an injury on his or her arm, they can move they can rehabilitate through this kind of devices. And also more and more we see devices that are telemanipulated, and then there's, so you manipulate, so for example in surgical robotics, this very famous robot, the Da Vinci robot, it has a haptic interface where you can feel the tissue as you make contact with it. It has a feedback in force that the operator senses as it performs a surgery, for example. So here is just an example of a robot milling, and here it's a huge robot, and I think this is just a PR video for KUKA, and so a public relations video, and it's just milling entirely a canoe. So of course there might be better ways to do this, but this is just to showcase that if you have good interaction control on your robot, you're able to perform these kind of tasks, and then a manipulator, it's versatile enough to just adjust to different orientations to perform the milling actions of this to finally finish a canoe. And at the end, they show the canoe completely finished. Of course, from this to the previous step, there might be a gap, but some of the pieces that were there that were done by the manipulator. And another example of interaction, as I mentioned, it's related to haptic devices, and we're gonna see that this is done through a combination of impedance and admittance controllers. So in this video, you see that there's somebody designing a 3D object, and the device that it has there, it's called a phantom haptic device, and the operator feels the feedback of the force as it touches the object. So here you see that it's kind of drawing this, and there's a feedback towards the operator, and this kind of interaction. So this is mainly when you want to transmit feedback towards the operator, This is mainly based on admittance control. And when you want to act with the environment, usually you use impedance controller. And as I mentioned before, not only the use of haptic devices is to interact with 3D environments, also to get feedback from, let's say, a remote robot interacting with another with a surface that might be soft or hard, and you need to understand what kind of surface you're dealing with. So in the end, you need to perform this kind of interaction control strategies. And I am showing you this picture. I couldn't find a nice video of this one because it's really hard to visualize. So this is a dentistry simulator, and basically this is used. I know that in the University of Pennsylvania, they're using it, and this is developed by a company named MOOC. And actually, this is the same company that developed the actuators on our newest robots. So they have a very large area of expertise. And this specific system, what it does is that it creates a 3D hologram. You see that the person that it's on the left has a pair of glasses. So those are 3D glasses, like the ones you have in, like when you go to the movie theater and watch a 3D movie. Then there's this hologram that you can interact with, and the device, it's very similar to the Phantom. It makes you feel as if you were interacting with the teeth. And I had the opportunity to test one of this during my master's, and it really feels like you're going through the teeth. Now, when you're out of the hologram, the illusion goes away, but it's really well made, and now it's used in some universities to teach dentistry. To simulate, instead of going directly to the patients, the first step it's solving the problems in the simulator. So another application for impedance controllers, it's related to mobile of legged robots. So the robot, it's constantly in contact with the environment. So you need to actually compute the forces that you want to get. So the ground reaction forces that you want to generate. So basically what controls the robot, it's not necessarily your joint torque, it's the force that you apply on the ground. So we use these kind of strategies on our HiQ robot that dates from 2010. And this is also used in the animal robot from ETH in Zurich. And the newest robot of them, it's Animal C, which is the one that they are starting to deploy to industrial plants. And it also uses impedance control because it became the standard on legged locomotion in general. And we also use these kind of strategies in our newest robot, HiQ Real. And also Boston Dynamics uses impedance control and interaction control to regulate the ground reaction forces that the robots feel with the environment. So another basic application is related to wearable robots. And one example, it's exoskeletons. And there cannot be a more evident device for human-robot interaction than an exoskeleton, because the robot is directly in contact with the robot. So you need to regulate the forces. You don't want to exert a very large torque on a specific joint because you might harm the person that is using the device. So also interaction control techniques are used in exoskeletons. So there are many tasks of interest and objectives that you can have during a specific motion. And they usually require to accurately follow or reproduce the desired trajectories at the end effector. So, and sometimes these trajectories can be done at high speed. And these trajectories can be defined at the surface of the objects. We're going to see some examples later on. And then you also need to control the forces and the torques that are applied when you're in contact with the environment. So you can have a low or a high stiffness, and low means that you have a very compliant behavior. So you can basically push the robot and it will move in the direction in which you're pushing. Or you can also have a rigid stiffness. And if you push the robot, as we saw at the end effector of the previous video, you won't be able to move it if you have a rigid behavior. So some applications, so some examples is that you wanna control your forces so that you don't damage the environment or the robot itself. And here, for example, we have a robot holding an egg, which is a task that requires a precise control of the forces and torques that you're applying on the egg itself. Or another example in which you need to apply a very precise control of forces is when you want to apply forces or torques in a specific direction. So for example, if you're turning a crank, you cannot apply force just in one direction. You need to constantly change the direction of the force. And you can also see this when a robot is trying to open a door. You need to apply the force in a specific direction as well. And then for balancing tasks, for example, in legged robots, when you're moving, and then remember the example when we were doing the joint space, when we started seeing the gravity compensation, I showed you the video of Haiku walking, and then when it had the weight on, the center of mass was displaced, and it adapted the location of the center of mass. Actually, what it's doing, it's controlling its run reaction forces to reach a certain orientation, and then obtain balance based on the ground reaction forces that you're applying on the ground. So one task that requires both position and force control is following a contour. So what we mean by this, it's that, for example, you have a workpiece and then you want to polish it. So you need to follow a specific trajectory around the workpiece, and you also need to apply a certain force. So you need to measure both force and position at the end effector level. So here we have two examples. One is a finishing of a washstand, and the other one it's finishing a metal cabinet on the right. And you'll see that you need to follow a specific trajectory, but then you also need to apply a specific force in the direction, in the perpendicular direction of the motion. So using purely position control, as we do for motion, can lead to problems. And this can also be related to the fact that the motion is not free, so it's constrained by the surface itself. And if you don't take into account, you may damage the part or the robot if you don't have knowledge about the environment. Of course, if you have full knowledge about the environment, you can design a trajectory right on the edge, but this is is not a good approach because there are always disturbances, there are always uncertainty. So it is better to also have an extra feedback related to the force and the torque. And so here there's a sanding and polishing task with a robot. And then here you'll see that the robot first is, so here it's polishing. So here's polishing a work table. These ones actually required to be very, so what's it called? They have really low tolerances, this kind of tables, because these are the ones where you perform experiments. So we have one of these in our lab, and we use it to calibrate rotational torque, rotational motors, so of our joints. And if you don't have good tolerances of this kind of tables, you can have offset torques generated by the screws on the table. For example, you see that these small holes are used for, and these are used to hold things on them. And if these are not, let's say, if these are not properly polished, you might have a constant torque because the screw is not well aligned. And when you do calibration, it's very important that you know where all of your torques are coming from. So another example, it's an assembly task. And this is very interesting because, for example, this is an assembly of a gearbox. So the first step is to insert the inner part of a planetary gear into the outer part of the same array. And one way to find out if the teeth of the gears are matching, it's by measuring the force when you apply a certain motion. And once you find an equilibrium between the two forces, then it means that the piece is properly assembled. I couldn't find a nice video of this. I mean, there were some that you had like a really short piece of the video where you see this small turn motion to see if the pieces are matching, turning motion to see if the pieces are matching, but it was like 1 or 2 seconds. And in general, this kind of assembly tasks, so for example, in car assembly lines, when you assemble the total gearbox, and in some factories, this is completely automated. So it's only the robots doing that. There's a video of in a SEAT, in the Spanish car manufacturer, where they are completely assembling a gearbox just using robot manipulators. And the other part the other thing that you can do is have a collaborative task. So you have a person, let's say, placing the pieces in the right position for the robot, and the robot just is in charge of completing the assembly. So somebody takes the pieces and the robot completes the assembly. Another example of this, it's doing a deboring task. What I explained at the beginning, what deboring is, removing the metal or plastic shards of certain pieces. And here's an example of here in the Excellence Center, if Cecchina in Rome, in 2002. This is a collaboration with the company ABB. And here it's also a task where you need to track a trajectory in position, but also control the forces to, let's say, not damage the windshield. So this is the deburring of the windshield of a car. So we can have passive or active methods when dealing with interaction. So regarding passive methods, we add physical springs and dampers to our system, and they can introduce, they reduce the force in the interaction, and they increase the control, the stability of the controller, because you're basically relieving the responsibility of the controller to a physical element in the structure of the robot, and you can have an infinite force bandwidth in the controller. However, when we're talking here about flexibility, it's in terms of, let's say, changing your stiffness, like the flexibility to execute different tasks, not the flexibility of the link itself. And the problem is that once you assemble a robot with a spring and a damper array, you would need, if you find out that your stiffness is not the right one for a task that you're doing, then you would need to disassemble the robot and replace the spring and damper array. The other way that we can do it's using active methods, and this is using feedback control techniques. So the one that we're going to see today, it's direct force control, and it employs a feedback directly at the force level. And this requires for you to know what is the force at the end effector. Generally, you measure it with a force sensor, or you can also estimate it, but that makes the problem a bit harder. So you require, as I mentioned, a force sensor at the end effector, and there are some stability issues related to it. And also depends on the formulation that you use. You can also do indirect force control, and this is when you do control of force and position at the same time. And we can have a compliance control in this kind of category of active methods. We have an impedance control, and we can have admittance control, which is the complement of the impedance controller, as we will see in the lecture, at the end of the lecture next week. And there are also hybrid strategies where you control position in one direction, and in the other direction you control force. And this is generally applied when you have perpendicular directions in the force and in the position. It makes it easier if the directions are perpendicular. So the active methods are way more flexible because you can just change your stiffness through software online. So you can have an adaptive stiffness in your system. However, because you're adding an extra control loop for the force, there's a delay in the maximum in the control itself, and this reduces the maximum bandwidth at which you can control the force. So in legged robots, one key aspect when doing research on novel actuators is the maximum bandwidth that you can do in terms of force control. And we can reach bandwidths of 100 hertz in terms of force, and the higher the bandwidth you have, the better. That means that you can react to, for example, to disturbances or impacts way faster and in a better way. So one example of passive control of compliance with it's using what's called a remote center of compliance. So the idea is that, for example, when you inserting in this peg in a hole task, you're inserting a rigid element inside a hole. Sometimes, if the peg is not well aligned with the hole, then this generates a moment. So it generates a force, a reaction force at the point of contact, and then this generates a moment in a direction in which you don't want to go. So if the robot keeps pushing, then you may damage the part. So one way to solve it is by using this device called the remote center of compliance. And these kind of devices are made by a company called ATI. And they mainly work on end effectors and modules to improve end effectors. And it uses it's this one, as I mentioned, is used in assembly tasks. So this is the peg in a hole task, and it's typically placed between the wrists of the robot and the gripper to add this compliance to the end effector. So the RCC it allows to move in an axis perpendicular, and the newest ones also allow to have torsional compliance and compliance in the z-axis. I'm going to show you a video. And the forces that are generated due to misalignment, as I mentioned, can be compensated in a passive way by this array of compliant elements. So here's a newer model of this remote center of compliance called the Universal Compliance Compensator. It's made by the same company, and in this task, they have a magnetic gripper, and they are picking up objects from a box, and the objects can be misaligned with the gripper. So as you will see, there's a bit of compliance in at the Universal Compliance Compensator, and this is the set compliance that I was talking about. Then there's the lateral compliance in this direction, and there's also the torsional compliance, which it's this one. So you can compensate for misalignments with this passive element, which is placed between the gripper and the wrist of the robot. Now, an example of active compliance. This is one of the first research paper, well, one of the earlier research papers of our lab, where our colleagues developed an impedance controller for the leg of one of our robots. This was when in the first steps of when we were developing the controllers of our robot. And here at the beginning, you will see using the physical spring damper, so the passive strategy. And then we have our virtual spring damper strategy. So basically, we're applying torques at the joint level to reproduce the behavior of this spring. And you'll see in this video that they were able to reproduce the behavior of the spring with small differences. Using this was taken with a fast speed camera, so it's taking a lot of frames so that you can see in detail the similarities between the two of them. So I'm going to finish this lecture with this one slide on direct force control, which is, let's say, the predecessor to modern techniques used for interaction. So the goal is that we have a reference force that we want to track. So the idea is that we measure the contact force F, and if F is smaller than our desired force, we apply more force. If F is larger than our desired force, then we apply less force. It's quite of a simple control loop. So we define this F star control action, which is our desired force plus a K gain times the error in force. And then we can complement our control actions with all of the compensations that we've seen in the previous lectures. And we defined our joint torques as minus so we're mapping our F star to joint torques, and then we're compensating for the nonlinear terms in the dynamics equation. Notice that here we have a negative sign because this is the force applied at the end effector by the joint. So remember that in our equation, the term on the right hand side of the equation, the U, is positive, but those are the forces of the environment. So now that's why we have this negative sign on the J transpose F star. So our dynamics, and we are plugging in this tau on the right hand side of the equation, and our dynamics become this. So at steady state, which is, remember, we are getting our derivatives to zero, so q dot and q double dot become zero. So h with the joint velocity equal to zero leaves us with our gravity terms, and we end up with this equation. And our steady state error goes to zero with this. However, this kind of strategies, it leads to instabilities because when you don't take into account the model so there are also some reaction forces in the object that you're dealing with. So if you don't take into account how those ground reaction forces are going to behave towards the robot, then you can reach instabilities. Okay, so I would finish today's lecture now. Do you have any questions regarding? I mean, it was just mainly introductory, and so. But if you have any questions, just shoot. So, if there are no questions, then I won't be in the lecture on Monday. Still, I'm going to follow it online. So, and then the professor will be here on Monday. Okay.
Yeah, thanks, Octavio. I remember everybody that you should pull the latest version of Locosim. I'm still updating that. So just to be sure, to pull at the very last moment to have the most updated code. And next week, we after the lecture on orientation control, we will do the final labs that will put everything in that we explain in the course into the picture. So it will be very practical labs on control in the joint space and in the task space. Basically, we see everything we thought in these last lectures implemented on a 6 degrees of freedom robot. So they will be very useful for the understanding. And then if we have enough time, we also do some exercises that we will simulate the exam, basically exercises in the very last hours of lectures of Tuesday. Okay.
Okay. Then
So
see you all Monday.
see you Monday.
See you.